In this video, we discuss about the flow in circular pipe. In viscous fluid dynamics, this is also known as Huygens-Poiseuille flow. In the name of the fluid dynamist Huygens. This is diagram. This diagram shows the flow between a pipe. Here the side length is total pipe section is capital L. This diagram is show velocity profile. Here motion is due to a constant pressure gradient along the axis of the pipe. Let the axis of the pipe be taken as z axis along the flow, and here R denote the radial distance outward from the axis. Here the non-zero component of the velocity is Vz. So the equation of continuity in cylindrical polar coordinate system reduces to delta Vz upon delta z is equal to 0. Either or Vz is independent of z, and equation of motion reduces to delta p by delta theta is equal to 0, delta p by delta r is equal to 0. This is our equation number 2. So minus delta p by delta z plus mu del square Vz by del r square plus 1 by r delta Vz by delta r is equal to 0. So then this equation 3 is become d square Vz by dr square plus 1 by r dvz upon dr is equal to 1 upon mu into dvp upon dz. If we write dvz upon dr is equal to y, then this equation become dy by dx plus 1 by r into y is equal to 1 by mu into dp by dh. This equation is very linear differential equation, and its integrating factor is equal to r. So the solution of this equation is y into r is equal to integration of mu into dp by dz into r dr plus a, and solving it we get y into r is equal to 1 by mu dp by dz into r square by 2 plus a. This implies y is equal to 1 by twice mu into dp by dz into r plus a by r, or r dvz by dr is equal to 1 by mu twice mu dp by dz into r square plus a. This is our equation number 4. And then we again integrate it, then we get the Vz equal to 1 by 4 mu dp by dz into r square plus a log r plus v, where a and b are constant of integration and to be determined by the applying following boundary conditions. When r is equal to 0, the boundary condition is due to symmetry delta Vz upon dr is equal to 0. When r is equal to a, this is known as no slip condition, then Vz velocity component z is 0. So here A is the radius of the pipe. Solving the equation from then we get capital A is equal to 0 and capital B is equal to minus 1 by 4 mu into dp by dz into a square plus b. So b is equal to minus 1 by 4 dp by dz into a square. Put value of a and b from 6 and 7 in equation number 5. Then we get Vz is equal to 1 by 4 mu dp by dz into r square into minus 1 upon 4 mu dp by dz into r square. So Vz is equal to minus a square upon 4 mu dp by dz into 1 minus r square upon a square. This is our equation number 8. So for the maximum and minimum velocity, differentiate equation at with respect to r, then we get dvz by dr is equal to minus a square upon 4 mu dp by dz into minus 2 by r upon a square is equal to 0. So this gives r is equal to 0, and when if we get d square Vz by dr square, then this value put in, then we get this is greater than 0. So dp by dz is negative. So the maximum velocity occur on the axis of the pipe at r is equal to 0, and this maximum velocity is given that Vz maximum is equal to minus 1 by 4 mu dp by dz into a square. So Vz upon Vz maximum is equal to 1 minus r square upon a square. This is our equation number 10. So the average velocity over a cross section is given that Vz bar is equal to integration 0 to a Vz into 2 pi r upon pi a square into dr. So then we get it, and solving it we get Vz bar is equal to minus 1 by 8 mu a square into dp by dz, or Vz bar is equal to Vz maximum by 2. And the volume, this result is known as flow between a circular pipe, and this is applied in many scientific and industrial research. Thank you.